The next part of the lesson discusses a term called resonance. The Lewis theory localizes the electrons between the atoms that are bonding together. That simply tells us that when two atoms bond together, we find the electron density between the centers of those atoms. Extensions of the Lewis theory suggest that there is some degree of delocalization of electrons. That delocalization tends to occur if I have a double single bond coming back to the same central atom. This concept of not quite being a true single and not quite being a true double bond, but lying somewhere between, is the concept of resonance. This delocalization of charge creates a very stable molecule. Resonance structures continued. When there is more than one Lewis structure, for a molecule that is different only in the position of the electrons, they are called resonance structures. The actual molecule is a combination of the resonance forms, known as a hybrid. The molecule does not resonate between the two forms, though we often draw it that way. The reality is it's a combination between both of our pictures. For instance, in this molecule, we see sulfur, double bond oxygen, single bond oxygen with a lone pair. This is in resonance with a single bond to the left and the double bond to the right. Now keep in mind, we are not literally just flipping the molecule over to see its mirror image. We are actually changing the location of the double bond from the oxygen to the left to the oxygen on the right. The truth of the matter is, it's not this picture or this picture, but a combination between the two. Sulfur literally, as it connects in a resonance structure, you'll often see this little hybrid bond, a dashed line to represent the between structure. In other words, the solid line represents a single bond. We know a double line represents a double bond, but a dashed line in this particular structure is a hybrid between the two. It is, in bond length, shorter than a single, but longer than a double bond. A hybrid between the look. Ozone molecules are a prime example of a molecule that actually exhibits resonance. An ozone molecule, O3, is its structure, and we see an oxygen double bond O, single bond O. Not changing just by flipping around, not changing to look at a mirror image, but we can also locate the double bond to the other oxygen. So the combination between these two pictures is a resonance structure. To exhibit ozone in terms of a model here, they're saying, suppose we have a purebred German Shepherd and a purebred Labrador, and they come together to create what's called a hybrid, a combination of both breeds. Oxygen in ozone does the same thing. Notice the double bond is lying to the left in our first structure. The double bond is lying to the right. The combination between a double and a single bond is now going to be represented by this dashed line. So the resonance hybrid structure is, the true picture is between the two. It lies between a single and a double bond. Resonance structures must have the same connectivity. Only electron positions can change. Resonance structures must have the same number of electrons. Second row elements have a maximum of 8 electrons, bonding and non-bonding, although the third row can expand the octet because of those empty d orbitals. Remember that the formal charges must total the same. For a molecule it's neutral. For a polyatomic ion, it will come out to match the charge. So drawing resonance structures really is just as easy as moving the double bond around. Draw the Lewis structure that maximizes the octets, as in the structure for NO3. Nitrogen's placed in the center, and as you draw the Lewis dot structure, We had a double bond going to the left and a single bond going to each of the other oxygens. You can see that they assigned formal charges. Nitrogen ended up with a +1. Two of the oxygens ended up with a -1. And of course, this oxygen has a 0 formal charge. The only difference between this model and this model is the location of the double bond. The location of the double bond moved from the left to the right. Formal charge stayed the same all around. Keep in mind, we did not just simply flip this molecule in 3 dimensions. We simply moved the location of a double bond. I can also see a third possibility in this picture. The third possibility could show the nitrogen having a double bond north. So I could see 3 equal resonance structures. A double bond going to the left, or a double bond going to the right, or a double bond going to the top, and the others remaining singles. This particular molecule has 3 possible resonance structures. Here's a molecule, H2SO4. We would call that sulfuric acid. When I draw the resonance structure in the first molecule, notice that they're all single bonds, giving sulfur a +2 for a formal charge. Notice what I can do to alleviate that +2 and the -1s on the oxygens and get them all down to 0 if I expand the octet. I move electron pairs from atoms with negative formal charge towards the atoms with positive formal charge. Ideally, we'd like them all to have 0. Notice that sulfur has now expanded its octet, and it will do so to alleviate the formal charge. Sulfur now has 1, 2, 3, 4, 5, 6 electrons assigned to it. Lives in group 6A, so 6 valence electrons. 6 electrons are assigned to it, giving it a formal charge now of 0. But we've expanded the octet to alleviate a formal charge. Count the number of total electrons around the octet. 2, 4, 6, 8, 10, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Normally, we know that 8 electrons maximized, but here's an example where expanding the octet was done to bring down the formal charge. Even if it expands the octet, we want to do that so that we end up with a 0 on the formal charge. The better structures, as you're deciding, as you draw your structures and are trying to decide the best possible placement of elements, the better structures have fewer formal charges. Better structures have smaller formal charges. Better structures have the negative formal charge on the more electronegative element. Ideally, everyone has 0. If I cannot draw a structure where that happens, try to make this formal charge smallest number possible. And if I do need to replace a formal charge, be sure the elements closest to fluorine end up to have a negative formal charge. Practice says, let's identify structures with better or equal resonance forms and draw them. This molecule we decided was all set. Everybody had a 0, so that was good. H3PO4, we decided, had formal charges. Up on the oxygen was a -1, and on the phosphorus ended up to be